Let's talk about numbers. And first up, let's just talk about integers, which are the numbers that don't have a fractional component. And that's both positive and negative. We have three main standard types in SQL that we use for storing integers. There's small int, there's integer, and there's big int. And the difference between each of these types is the amount of storage they take, and therefore the maximum and minimum values they can contain. In the case of small int, that takes up 2 bytes of storage, and as a result, its maximum and minimum values are around plus or minus 32,000. For integer, it takes up 4 bytes of storage, and as a result, it can store a maximum and minimum value of around 2 billion. And for big int, it takes up 8 bytes of storage, and as a result, it can store extremely large numbers that are around the magnitude of 9 by 10 to the 18. Sometimes you'll see these types aliased with different names as well. Small int you'll sometimes see in databases called int2, integer you'll see int4, and big int you'll see called int8. Let's look at our entity relationship diagram, and let's have a look at the different integer types that we're using. Looking at this customer table, you can see we've got the store ID as an int2, that's a small int. The customer ID is an int4, that's just an integer. And there's an address that's also an int2, and an active flag that's an int4. I mentioned in an earlier video that typically you want to pick the type that accommodates the kinds of values that you're going to store, but also minimizes your storage requirements. So in this case, the store ID is an int2, it's a small int, which means it can store up to a maximum value of around 32,000. So that must mean that the database designer was confident that there would never be more than around 32,000 stores in this database. Because if you try to store the value, for example 35,000, in an int2 column, it will fail, you'll get an error. So this designer must have been confident that there would never be more than 32,000 stores. When you're designing your own database, therefore, you have to put a little bit of foresight and think about what is the maximum possible value that you want to store in a given column, and pick the right kind of type to accommodate that. Operations between integers work pretty much as you'd expect, and you've actually already been doing it a lot. In past exercises, you've been doing addition, multiplication, and division between integers. But there's one thing that can catch you out when you're working with integers, and it leads to actually a bit of a broader topic that I want to talk about. I'll do a quick demonstration first, and then I'll explain what happened. Running that, we get the result of 1. So what I've just done here is just a single select statement where I'm using SQL like a calculator, and I've done select 3 divided by 2, and the result was 1. This actually might surprise you a little bit if you're not familiar with the concept of data types and integer division from other programming languages. What actually happened here is that when you have an expression that involves the same types, so here we're working with integers, we're saying 3 divided by 2, the result of that expression is also an integer, which is unable to store a fractional component. In Postgres, you can actually use the function pgtypeof to look at different types as well. So if we wanted to, we could type out select pgtypeof 3. We'll do that as our first column. As our second column, we'll do pgtypeof 2, which should be unsurprisingly an integer as well. And then we'll look at the type of the result of 3 divided by 2. Let's run that, and it's telling us that 3 is an integer, 2 is an integer, and 3 divided by 2 is also an integer. And that's why we get the result of 1. The fractional component of the true result, which is 1.5, has been truncated, and we're just left with 1. And so this broader topic that I actually want to talk about is about casting and type coercion. When you have an expression that involves the same type, then you just get the same type as a result. So here we had integer, 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 integer in, and integer out. But if you have an expression involving different types, what can happen is something called type coercion, where one type will be converted to the other type. And it's a sort of implicit conversion behind the scenes. You didn't have to do anything or specify anything for that conversion to happen. Let me give you an example where what I'll do now is I'll do select 3.0 divided by 2. And I'll run that and I get the result of 1.5. And that's because 3.0 is actually a numeric type. If we do select PG type of 3.0 and we run that, the type is numeric, which I'm going to talk about in a little bit. It's one of the types that supports fractional components. So here, when we've done select 3.0 divided by 2, what happened was that this 2, which is an integer, was automatically coerced or cast to a numeric. Sometimes this is called type promotion as well. So this 2, which is an integer, was promoted to a numeric. You may not have been aware of it so far, but you've actually been making use of type coercion all throughout this course. Another example of type coercion is when you have an expression where you're combining strings and numbers. So if you concatenate, for example, hello with the number 2, the integer 2 here was actually coerced behind the scenes to a string, to a text type. If you want to be explicit though, and to tell SQL what different types you're working with, you can use casting. And there's a couple of different ways that you can achieve casting. Let's say that I wanted to tell SQL that the string that contains the text 33, the number 33, is an integer. And that's something that SQL can do. If you've got a number inside a string, it's able to convert that to an integer for you. You just have to tell it though that you want to treat that as an integer. So let's go ahead and do that. I'll show you a few different ways that's possible. The first is with what's called a decorated literal format. So if I want, I can say int, and I'll put 33 as my string. Another way I can do it, which is actually Postgres specific, is by using this double colon operator. And I can say treat that as an integer. And then the third way I'm going to show you is what's called the standard format, the standard way of casting. This will work across a variety of different databases. You can say cast 33 as in. And I can run that. The type of each of the outputs is int4, so it was correctly cast to an integer. And you can just hover over this icon in the top left corner. Notice how each of them is an int4, an integer. And so this is 3 different ways to achieve exactly the same thing. All of these is equivalent. This third form is the standard form, but it's also the most verbose. So sometimes throughout this course, you'll see me using this form, and I like this form because it's nice and succinct and compact. Throughout this course, you've actually seen me several times already making use of either type coercion or explicitly casting something. In an earlier exercise, we did something where we were calculating the percentage of customers with an email address. And I'm just going to paste in the query that we used to do that. Running that query. So this was an exercise where we were calculating what percentage of customers have an email. The count function actually returns an integer. So if you just do count email divided by count star, you'll be doing integer division. And if you multiplied that then, let's say by 100, we lose our fractional component because we're doing integer times integer divided by integer. We're just doing integer math, which is unable to express a fractional component. So what I did was I multiplied by 100.0. If you have 100.0 out there on its own as a literal like it is, that's actually a numeric. It's a type that's capable of storing fractional components. So now what will happen is this expression will be evaluated as 100.0 multiplied by the count. So this will all be automatically converted behind the scenes to a numeric, and then that number will be divided by the count, which will also be promoted to a numeric. The net result is that the entire expression is evaluated as a numeric now. And we get a result that can express fractions, 99.666. We also did an exercise where I did some explicit casting, and in the description for that exercise, I mentioned that I would explain it. Well, here's that explanation. So I'll paste in that exercise, and I'll run that. And this was that really interesting exercise where what we were doing was creating a sort of histogram showing how many different films have different MPAA ratings. And you'll notice in the solution here that I'm performing an explicit cast to an integer. And the reason why I'm doing that is because technically the count function actually doesn't return an int, it returns a big int. And so this entire expression evaluates to a big int. The 10 is promoted to big int. If I don't have this explicit cast in here and I try to run this, I get an error. And that's because the repeat function expects a string or some text that it wants to be repeated, and then an integer, but I'm trying to pass in a big int. So I have to override the result of this expression and I say, no, treat this as an integer. And now I can run that and that works. So throughout this course, as you're working with different functions and you're using different expressions, be aware of the different types that you're using as arguments to your functions or expressions, and be aware of the resulting types that come out of those expressions or functions. Sometimes you may need to introduce casting or explicit type coercion to get the kind of result that you want. Okay, so that covers the integers. Let's now talk about numbers that do have a fractional component. Numbers that have digits after the decimal point. With SQL, we can divide these into two types, exact and approximate. And they're sometimes also called fixed versus floating point types respectively. And how they primarily vary from each other is actually how they store the number. For exact, there's really only one type, and it's called numeric. And when you specify numeric, you also have to provide a precision and a scale. Sometimes you'll also see this referred to as decimal. And decimal is the same. Decimal and numeric are identical, they're equivalent, in just the same way that int4 is another way to refer to integer. So throughout the rest of this course, I pretty much will always just use numeric. When you make use of the numeric data type, you have to provide two arguments, the precision and the scale. What the scale refers to is the number of digits after the decimal point that it's able to store. So if, for example, you see a column specified as numeric, let's say 5, 2, what that means is after the decimal point, this type is able to store 2 digits. So 0.50, 0.99, 0.00, whatever that is, it can't store more than 2 digits after the decimal point. So that's the scale, that's what the scale refers to. And what the precision refers to is the total number of digits that this type is able to store. So numeric 52 says you can store 2 digits after the decimal point, and you can store 5 digits total. What that means then, because we've already used up 2 after the decimal point, we have 3 left over to appear before the decimal point. So numeric 52 can store up to 999.99, and it can store 000.00, it can store numbers in between like 32.76, it can store 351.03, but it can't store 4000. Why can't it store 4000? Because 2 digits are allocated after the decimal point, so that's in this case 0.00, and we're using now a total of 6 digits, but we're able to only store 5. Let's have a look at our relationship diagram again, and let's see where we're using numeric. We can see for the payment table that we're storing the amount as a numeric, that's 52. Let's scroll down and see where else we're using numeric. For the rental rate for films, we're storing that as a numeric, 42. And for the replacement cost, we store that as a numeric, 52. To contrast though against numeric, which is the fixed point type for storing numbers that do have a fractional component, there's also the floating point types. And the main floating point types that you'll come across are real and double precision. Real can store up to 6 decimal digits, and double can store up to 15. With these types, what's different is the way that the data is actually stored. Rather than storing a fixed number of digits of precision or scale before and after the decimal point, here, for these types, the decimal point can actually float, and they store the actual digits of the number and then just an exponent. The floating point types can save space versus the numeric type, and sometimes they're actually quite a bit faster in calculations as well. I already gave away the trade-off though when I was talking about the naming. With numeric, it's called an exact type, and with real and double precision, they're called approximate types. And the reason why we call them that is because you can get imprecision or error that's introduced into your calculation when you're using the floating point types, and that comes as a result of how the numbers are stored. Let me give you an example of that. So I'll do select, and what I'll do is I'll do 0.4235, and I'm going to cast that as a numeric of precision 5 and scale 4. So it's able to store 4 digits after the decimal point, 5 in total, and I'll multiply that result by 10 million. Now let's compare that with using a real. So I'll use 0.4235, and I'll cast that as a real, and again, I'll multiply that by 10 million. Let's run that, and let's have a look at the result. When I was using the numeric, the result is exactly what you would expect. 4,235,000. When I was using the real, however, I got something that's quite close to the exact result I expected, but not exactly. There's this other fractional digits that were introduced. That's the error. And it's just an inherent part of that storage type. If you're using real or double precision, due to the way that the numbers are stored on disk, calculations with them can introduce small errors. As a general rule of thumb, just due to the error inherent in using floating point types, I will probably recommend that most of the time you use the numeric type, unless you have a very good reason to use a floating point type. Lastly, just to round out this video, let's have a look at a couple of the common math functions and operators that are available to you. You've already been using quite a few of them throughout this course, so these are the functions and operators that operate on numbers. And if we scroll down, I'll just draw your attention to a couple of functions that are interesting and you'll find yourself using quite often. There's the ceil function, which will essentially act to round any number you give it up to the nearest integer. By contrast, there's the floor function, which will round down to the nearest integer. And then there's the general round function, which based on the number will round up or down to the nearest integer. There's the power function as well, which you can use to raise a number to a particular power. There's log functions as well. And there's also, if you scroll down, the trig functions as well. So if you need to make use of the sine or cosine function, these are available as well. One last thing I'll just point out is whenever you're using functions, always just be aware of the type that they expect as their argument. So you can see a lot of these functions will accept numerics. DP here stands for double precision, so round will accept a double precision or a numeric. And with all the functions as well, you can have a look at the return type column and see what kind of type they return as well. So in summary, when it comes to the numbers in SQL, you've got the integers, small int, integer, and big int. And for storing numbers with a fractional component, you've got the fixed type, which is numeric, or you've got the floating point types, which are real and double precision. Always prefer to use integer if you're storing numbers that don't have a fractional component. Next, generally speaking, you'll want to use numeric if you are storing something with a fractional component. And then you can also use real or double precision if you don't need calculation accuracy and you don't mind a little bit of error being introduced in your calculations.